Hi everyone, I'm Ryan Honeyager and I lead the Numerical Weather Prediction Division at Tomorrow.io. Today I'm going to talk to you a little bit about how we can use the Tomorrow Microwave Sounders, or TMS, in a few different applications. So, to recap from Joe's talk, TMS represents a series of small satellites in several low Earth orbits that collectively provide global sub-hourly coverage. This enables rapid refresh applications and greatly helps with any other activity that benefits from large amounts of satellite data. But how do you actually use TMS in those applications? Many of your applications will be agency or organization specific, but they do have a few common patterns. Our science staff are developing many different reference examples that can speed up your own evaluations and integration. So let's start with some overpass applications and a little bit of nowcasting. And for this, let's just look at tropical cyclones a bit because they're always wildly fun. So TMS is primarily a microwave sounder, and by virtue of being a microwave sounder, it allows us to peer inside of clouds and infer vertical profiles of temperature and water vapor, and you can even retrieve precipitation properties to a certain extent. So TMS sounding channels have sensitivities that peak at different heights in the atmosphere and even at the Earth's surface. So just from a colorimetry perspective, we can assign colors to these and create composites to show details of storm structures. So here is an overpass of Typhoon Sinlaku, which was a Category 5 tropical cyclone which impacted Guam earlier this month. The swath here is about 2,200 kilometers across. So our window channel composite in the center shows precipitation, convection, and areas with low humidity. The composite to the right presents a view of moisture in the upper troposphere, which is also shown alongside a proxy for storm top heights. TMS can resolve brightness temperature anomalies, and it can even infer the warm core structure of the storm. So diving in a little bit deeper, let's just say it's a lot of fun to watch sequences of microwave overpasses as storms evolve. Here's another recent example from Cyclone Narelle, which had 4 separate landfalls over Australia. I think this might actually be the record. And over 10 days, TMS had 84 direct overpasses that resolved the full cyclone, and they occurred at all different times during the day. Now, that's actually comparable or similar to the total number of overpasses from US based and EUMETSAT hosted sounders, but given the orbits of the satellites, TMS observations do tend to be very evenly distributed, whereas for the US EUMETSAT constellation, the observations do tend to be clustered at particular times of the day. And you might wonder why that is. So here's what I mean by this. Here are 2 different views of where our satellites are positioned versus other satellites in the observing system, and this provides a little bit of context of why TMS satellites are very useful. Most microwave sounders have historically been launched into sun-synchronous orbits, and that means that these satellites pass over the same points on the ground at the same times each day. To the left is a clock plot which shows the equatorial overpass times in UTC. You can see, based on the satellites, sometimes they look like they're clustering around 2 or 3 orbital planes, and that's really what's happening here. Now, TMS has that too. We're matching common orbital planes for cross calibration, but in addition to this, TMS is also deployed in inclined orbits that precess each day, and they fill in the gaps inside of the observing system, so we always will have overpasses. So the various satellites do strongly complement each other, and since we always have a recent microwave overpass, we can peer inside of clouds, and our precipitation estimates should always exceed scale from geostationary only observations. And that's what I'm going to highlight here. In one of our recent papers, we showed the development behind our nowcasting algorithms. We're able to fuse microwave and geostationary vis-IR observations to improve precipitation retrievals. Traditionally, these have only been done through geostationary observations because it's very hard to have a low Earth orbiting satellite pass over a cloud at the right time and have enough overpasses to make a robust retrieval and see how precipitation is evolving. By adding in microwave, you can not only see inside of a cloud structure and get a better precipitation retrieval, but with a rapid refresh microwave constellation, you can do this all the time and you can establish a bit of a time value behind our observations. For TMS, that time value is about 70 minutes, which means that our high key skill scores for precipitation forecasting are exceeding those of a geostationary only retrieval for about 70 minutes post observation. Given that our global median revisit rate is now sub-hourly, we actually now have large periods of times for any storm system where we never have to fall back to pure geostationary skill. So we're able to make a better precipitation forecast, we're able to make a better nowcast with these satellites, and ultimately we can produce better weather insights. Now, beyond precipitation detection, I'll highlight SIMS at the University of Wisconsin, and they are estimating tropical cyclone intensity using data from TMS alongside other microwave sounders. That team runs a public facing operational website that tracks cyclones globally, and TMS data already account for half of all observations. That helps greatly with catching rapid storm intensification events, which in our evolving climate happen with increasing frequency. And I'll say that this study is ongoing, and we're excited for future developments in the upcoming Atlantic season, which is about to start. So let's also talk a little bit about data assimilation. This is one of those capstone integration activities, and TMS really is a sounder that's tailored towards temperature and water vapor retrievals. So data assimilation is a great application because of that global coverage and its decent calibration. So there's many different possible ways to assimilate TMS into a model. Scientists have historically taken clear sky approaches. There's been some recent development in the all sky community. There are frequent discussions about thinning and superopping, which really, from a certain point of view, is a type of averaging, and on developing appropriate quality control methods for the observations and developing appropriate bias correction models. My group has a recent paper published in QJRMS that describes the methodology behind one approach to accomplish this, and it's intended to be a reference for the field to accelerate uptake. So what does that mean? Say that you're a small to mid-sized satellite agency and you want to investigate TMS. This acts as a potential starting point. And to do that, we've aimed for maximum applicability. We built this reference using the Joint Effort for Data Assimilation Integration, or JEDI, which will power operational data assimilation at many different agencies, from the US-based ones through the UK Met Office and beyond. It's starting to roll out into production just now. And JEDI works with the FE3 model, it works with MPAS, LFRIC, many others, and it also supports common observation operators like the Community Radiative Transfer Model, or CRTM, and also RTTOV. With JEDI, we can convey the instrument science as a set of human-readable configuration files instead of as machine code. So you don't necessarily have to have a software engineer looking at the code trying to work out what it does. An actual scientist can take a look and can understand how and why this assimilation method is working. So as part of the study, we actually build up a cycled reference system that is loosely paralleling NOAA's Operational Global Data Assimilation System, or GDAS. And it's designed to provide a simplified baseline with the resource requirements that are within range of a mid-sized academic or a small government agency. That being said, it is ingesting real observation data from NOAA's observation processing system, and it does also rely very heavily on the Environmental Modeling Center's efforts to migrate to JEDI from the GSI code. It's using the same non-TMS instrument configurations. It's just using a more simplified data assimilation setup. And as part of this experiment, we developed the TMS assimilation by following a fairly standard methodology. We're using an innovation-based diagnostic scheme to approximate TMS's observation error variances, and we do this on a per-channel basis. We establish clear sky filters, and then we also establish an all-sky model using an approach that was originally designed for the infrared community but is seeing increasing application in the microwave field. For details here, see our paper. We do have a set of experiments, and we are basically running data denial cases from some control. Our control has all available observations in our observing system, both TMS and non-TMS. And then for data denial, we're removing microwave observations from different satellites to establish the impact. So for example, we can take our control and remove 2 TMS satellites. We can also take the control and remove 2 instruments of any other system, including, say, the Advanced Technology Microwave Sounder, or ATMS, which is the flagship microwave instrument that NOAA has deployed up till present. So we're considering small numbers of data denial cases, but it's enough to establish some trends. So here are 2 plots of 6-hour forecast impact. The temperature is on the left, water vapor is on the right, and I show here both TMS and ATMS data denial cases. At first glance, you can see that the instruments are comparable. And by that, what I mean is that they behave similarly, and they behave in a very physical manner that reflects their underlying build characteristics. You need that consistency. It's really important, and establish some expectations for performance. So the ATMS instruments, so the Advanced Technology Microwave Sounder, are much larger. They have a larger sensor, they have lower noise, they're designed for a very robust build, and In particular, for temperature channels, they're looking at lower spectral frequencies than what our TMS instrument is looking at. So that means that the footprints are a little bit different and the bandwidth per channel is a little bit different. And you can see how this comes through for temperature. Still, TMS does have some temperature impact, particularly where there are no ATMS observations, because again, it's only in one orbital plane. For water vapor, however, you can see that we're actually much closer in terms of performance. And this reflects fundamental physics. Our footprint sizes are very similar, the bandwidth is very similar, and so is the fundamental instrument noise. So you can see that TMS establishes a very similar impact across your troposphere. Our impact skews a little bit higher because our sounding channels have slightly higher peaks, but that's also physical, and the overall impact is what we expect, especially given our calibration studies and external evaluations. So we can run this out for a few days to gauge if the impact still persists, and it does. Here are TMS and ATMS data now cases at different lead times and pressure levels, and you can see that the behavior is what we expect. Impacts are significant out to around 3 days, after which our own error becomes more dominated by model level effects. Again, we're running a more simplified data assimilation system, and that is totally expected, but in an operational setting, we expect this impact to persist a little bit longer. Now, you might wonder how we're validating all of this and how the observations and instrument science can be integrated into your systems. So, two different things here. First, we have several recently published papers that have some bearing on the subject. Joe Munchak's paper is in preprint, and this first one discusses the TMS pre- and post-launch calibration procedures, and it discusses calibration accuracy in terms of geolocation error, and it also discusses radiance validation, where we look at bias and we look at the standard deviation and other noise characteristics like NEDTs. This establishes our performance expectations. Outside of that paper, we have considerable material describing each satellite's calibration status. Garrett et al., our second paper here, describes that all-sky simulation approach, and it presents the impact study that I briefly walked through. There's a lot of content there. It's an open access paper. We again hope that you'll be able to find a lot of insight from this. Forrest Cannon's paper establishes our precipitation retrieval algorithms and discusses that time value of observations and overall skill. Beyond this, we do have many other white papers, many other presentations available, both internally and externally, and we also are working on several new manuscripts that should be entering peer review later this year. Beyond just our own publications, there are some independent evaluations that are either ongoing or have recently concluded that I can highlight. So the first of these is the NOAA Commercial Microwave Data Pilot. The goal of this pilot is to integrate our sounders into relevant NOAA workflows and products and to assess their performance. So for this pilot, we have delivered data from several satellites for many months now, and this is real-time data delivery as soon as we acquire the data from the satellite, so as soon as we downlink. So observations flow to NOAA, and then they can use them in systems like the Microwave Integrated Retrieval System for assessments. They've used them with AWIPs. They've used them in other places too. NOAA does sponsor a very large evaluation group composed of scientists from several national and international agencies. So other groups have access to the satellite data as well for the purposes of this assessment. Now, I'll say that the evaluation is still in progress and NOAA's conclusions are their own, but NOAA staff have given many public talks recently. An overview was presented at this year's annual AMS conference by Sherry Pan. I have the citation down below, and we're looking forward to the release of any final reports. Beyond that evaluation, the Joint Center for Satellite Data Assimilation, or JCSDA, also conducted their own independent evaluation for the U.S. Air Force. This is the same group responsible for core JEDI development, and they assessed 4 TMS satellites over a 6-month period using primarily the model for prediction across scales, or MPAS, and also a little bit of FE3. So they assessed a few data simulation configurations, one of which was very similar to what we proposed in our paper, and they also noted a robust increase in forecast skill. There are other ongoing DA studies at NOAA, NASA, and other agencies, plus several for the preceding tropics instrument, and we can provide more specific updates on request, but overall, we think that TMS is doing very well, and TMS impacts or TMS-like instruments will become a mainstay in the global observing system. Anyways, thank you for your time.